We said in the last section that a differential equation is an equation that contains a derivative. And we have some experience already solving differential equations. That involves finding a function whose derivative is the derivative we've started with, and maybe also we need that function to meet some other criteria, like it contains a certain ordered pair. So far, the only differential equations we've solved are ones where the derivative expression is on one side of an equal sign, and on the other side of the equal sign we have a function just of one variable. So we want to now try to solve equations that contain derivatives of more than one variable, sort of like undoing implicit differentiation back from chapter 3. So we're going to focus on a very specific class of differential equations. It's what we call a separable differential equations. That means we're going to be able to use regular algebra to move all of one variable to one side and all of the other variable to the other side. Well, most of the time these equations are written in terms of x and y. We're going to try to move all the y's to the left and all the x's to the right. Then our technique is to use integration, so to find antiderivatives to solve differential equations. So watch what happens here. This is example 1. I revised it slightly. Let's see if this works. Oh, there we go. All right. There, I'll cover up my steps. So here I have an equation. It's a differential equation. It contains the expression dy dx. And on the other side, I have this expression x squared y squared. So this is my first time where I have a derivative. It's given in terms of both x and y, and I'm supposed to find what y is. So our first job is to try to decide if this is separable. Can I move all the x expressions to one side and all the y expressions together? So in this case it is. I'm going to, my technique always, pretty much always, when I have a dy dx differential equation, is to multiply both sides by dx, and then to divide by whatever a function of y I still have on my right-hand side. So here, I'm going to think of this kind of like, I'm going to multiply both sides by dx, and then I'm going to have dy is equal to x squared y squared dx. I'm trying to get all my y's and dy's on the left-hand side, but I see I have this y squared term over here, so I'm going to divide both sides by y squared. So now I've got dy over y squared equals x squared dx. If your differential, that's the dx or the dy, or it might be some other variable, ever ends up in a denominator, something has gone really wrong and you have to go back and fix it. You always want to get the y's on the left, the x's on the right, until you go to college and take a class called differential equations. New rules there, but for our purposes in AP Calculus, when we solve separable differential equations, we want to get all the y stuff on the left, all the x stuff on the right. Because the reason I can't have that differential in the denominator is because I'm supposed to have what looks like an integram. My next step is going to be to integrate both sides. So you never saw dy in a denominator in an integral, so it just doesn't happen. Because remember, what does it mean? It's supposed to be that very small change in x that you're multiplying by that gave us the original definition for definite integral. So here I have, am I ready? Now that I've separated my variables. If you got this far on the AP test, you get 1 point. You got all the x stuff on one side, all the y stuff on the other side. Our next step is to integrate. So that really just looks like slapping an integral on both sides. So my new equation, the antiderivative of dy over y squared is equal to the antiderivative of x squared dx. So my next step, I'm going to actually try to find those antiderivatives. So on the left side, I'm going to think of that as y to the negative 2. So to find the antiderivative of y to the negative 2, I'm going to use the inverse power rule. I'm going to add 1 to my old exponent and divide by the new exponent. So negative 2 plus 1 is negative 1, and I'm going to divide by negative 1. I'm going to get negative y to the negative 1. On the other side, I'm going to have the antiderivative of x squared, x cubed over 3. And notice that for each of those, I'm going to need a plus c. Well, we're about to go through this process about 100 times over the next couple of weeks, solving separable differential equations. And if every time I integrate on both sides and I need a constant on both sides, the first thing I'm going to do is try to move the constant from one side to the other. So what we generally do is, instead of using a constant on both sides, just say, okay, I already know I'm going to move the constant over and make some kind of new constant. So we write one constant over on the left. That shouldn't have there shouldn't have a subscript there. We generally just use c, and you're only going to need it on one side. So negative y to the negative 1, that's the same as negative 1 over y, is going to equal x cubed over 3 plus a constant. If you got this far on the AP test, it's worth 1 point for remembering your plus c. It's probably worth 1 point for getting your two antiderivatives right. If those antiderivatives had been more difficult, if they weren't ones that you could just do in your head, they might have been worth 1 point each. So if you find a separable differential equation problem on your AP test, that's typically worth 5 or even 6 points. So the more progress you can make through it, that's a lot of points that you can rack up. So my job here is to figure out what the original y function was that made the original differential equation true. So I have two things left to do now that I've integrated on both sides. I'm going to try to isolate the y, so undo all the stuff that's happening to y to get it by itself. And I also have to figure out what c is. I'm going to use that ordered pair that they gave me at the beginning to figure out what c is. The order that I do these two things does not matter. If you accomplish either one of them separately, they're each worth a point. If you accomplish both of them, then that's 2 more points that you can get here on this problem. Most of the time, I end up trying to find c next. Again, it does not matter. So if you decide at some point that you'd rather isolate y first and then figure out c, that's fine too. So I'm going to continue by trying to find c. All right, so this is what I like to do next. I've been told at the beginning that when y is equal to 1, x is equal to 1. So I'm going to come over here to the side, and I'm going to figure out what c is by using this ordered pair. So negative 1 over my y is 1 is supposed to equal 1 cubed over 3 plus some constant. I'm going to figure out what the constant is. So this is negative 1 is equal to 1/3 plus c. And I'm going to subtract 1/3. At this point, you can do as much or as little work as you care to. They're just going to check for the final answer. This is negative 4/3 equals c. So now I'm going to take that c that I got. I'm going to go back to the equation I was working with. Negative 1 over y is equal to x cubed over 3 minus 4/3. All right, so that is 1 step away from the final answer, 1 point shy from the total possible. If I want to get the last point, I'm going to have to isolate the y. A couple of options here. Really, so you can do whatever algebra you can think of to do, as long as it's legal. I'm going to probably multiply this whole equation by negative 1. So I'm going to get 1 over y is equal to x cubed over 3 is going to become negative, and 4/3 is going to become positive. I'll probably write that as 4/3 minus x cubed over 3. I notice that my left-hand side is a fraction with y in the denominator, and I really want y to end up being in the numerator. I'll just mention this as a word to the wise. It would be a common error to think you could just flip everything over. You can flip both sides of an equation. You can like reciprocate both sides of the equation if each side is exactly one fraction. So that's the technique I'm going to use. I'm going to rewrite this as 1 over y equals 4 minus x cubed over 3. Now I can flip both sides. So that's going to be y equals 3 over 4 minus x cubed. This is my final answer. I want to call to your attention some things you could do to check your answer. Given that this problem is going to be worth more probably than any other problem on your whole AP test, you might like to take some steps to make sure you haven't made any silly mistakes, because you'd hate to lose those points. So here's a really quick, easy one. You have to make 100% certain that 1, 1 is an ordered pair on this graph, because they told you that at the beginning. So I'm just going to test that 1 should equal 3 over 4 minus 1 cubed. 1 should equal 3 over 4 minus 1 is in fact 3, and 3 divided by 3 is 1. So that's one way to check. It's not a foolproof check, but at least lets you sometimes find an error. You can go back and try to find that source. The other thing you could do is to take the derivative of both sides of this equation. You'll have then an expression for dy dx, and you have an expression for y that you can use, and you can see if you can recreate the original equation as a true statement using combinations of your y and your dy dx. That takes a lot more work, and it's not sometimes not easy to do, but if you really want to guarantee that you have the correct solution to your differential equation, that's going to be your technique. So let me just show you what that might look like here. All right, where's our original differential equation? Here's my solution. I'm going to take the derivative of both sides of this equation. Before I do, I'm going to rewrite this so that I can use the power rule instead of the quotient rule. I'm going to write that y is 3 times 4 minus x cubed to the negative 1. Now when I take the derivative of dy dx, that's equal to 3 times negative 1 times 4 minus x cubed to the negative 2 times the derivative of the inside, which is negative 3x squared. So I'm going to try to make this look like this. So check this out. I'm going to say dy dx is equal to this negative and this negative cancel. So I don't have any negatives left. This is going to be 3 times 3 is 9, x squared in the numerator. And that's 4 minus x cubed squared in the denominator. So that is the same as 3 over 4 minus x cubed squared times an extra x squared. So 9 is 3 squared. 4 minus x cubed all squared is 4 minus x cubed squared. So check this out. Remember that 3 over 4 minus x cubed was y? So that's y squared x squared. And I just proved that dy dx is equal to x squared y squared, which was my original differential equation. That confirms for me, if I take that together with the fact that I already checked that 1, 1 is an ordered pair on this function, that confirms for me 100% that this is the correct solution to my differential equation.